This is an example for the regenerative Rankine cycle. Okay, the question is steam power plant operates on an ideal regenerative Rankine cycle. So you have ideal regen Rankine cycle with two open feed water heaters. Steam enter the turbine at 10 megapascal, 600 degrees Celsius, and exhaust the condenser at 5 kilopascal. Steam is extracted from the turbine at 0.6 and 0.2 megapascal. Water leaves from feed water heater as a saturated liquid. So this is the keyword there. Water leaving the feed water heater as a saturated liquid. The mass flow rate of steam through the boiler is 22 kg per second. So you have m dot. Show the cycle on the TS diagram and determine the net power output and the thermal efficiency. So the schematics diagram for the system is as shown in the figure here. Okay, you have steam enter the turbine. It mentioned from the statement here. Let's say we put in some numbering. Okay, usually after the condenser, okay, the steam goes to the pump. So let's say this is point number 1, and then exiting the pump, the first pump is point number 2 into the feed water heater. Okay, both feed water heaters are open. Okay, the statement from the question say two open feed water heater. So number 2 to number 3, number 3 to number 4 in the pump, point number 4 to number 5, okay, in the feed water heater. Number 5 to number 6 is in the pump. 6 to 7 is in the boiler, and 7 it goes to 10. 7 it goes to 8, extract some steam. 7 it goes to 9 as well, extract some steam. Okay, so Y fraction of mass goes to feed water heater number 2 here. Okay, and then Z fraction of the mass goes to feed water heater number 1 here, and the remaining goes to the condenser. So if this is 100% or 1, the steam that enter the turbine, Y goes here, Z goes here. The remaining would be 1 minus Y minus Z. Okay, and then if you follow the flow of 1 minus Y minus Z, it will combine with the Z again in feed water heater number 1. So after combining with the Z, it goes out from feed water heater number 1 with the mass of 1 minus Y. Okay, 1 minus Y minus Z plus Z equals to 1 minus Y. And then 1 minus Y goes to the feed water heater number 2, combined with Y, and then the remaining is 1 or 100% of steam. It goes to the boiler and it repeats the cycle. So this is the schematics for this question. Okay, and then how to sketch the TS diagram. This is our TS diagram. Okay, so we have two feed water heater. Okay, and then from the question, it says 10 megapascal is the highest pressure. the lowest pressure is in the condenser, 5 kilopascal, and then the middle pressure, you have two pressure because we have two open feed water heater, 0.6 and 0.2 megapascal. So you have 4 lines of constant pressure. The first line is at the top one, which is 10 megapascal. The lowest one is 5 megapascal. And then you have 0.6 megapascal is in one of the feed water heater, and 0.2 megapascal in the other one. Okay, and then another keywords that is given from the question is that water exit the feed water heater as a saturated liquid. Saturated liquid, the location is here at point number 1, point number 3, and point number 5. Those are saturated. So if we refer to, okay, we start with number 1. 1 to 2 is in the pump. So it pump from one pressure, the lowest pressure, 5 kilopascal, to the second lowest. So 1 to 2, it goes from here to here. Okay, and then from 2 it goes to 3. From 2 it goes to 3. Okay, where it combined with the 9. 2 to 3 combined with the 9. Okay, 9 coming from the steam turbine. Okay, and then 3 it goes to 4. From number 3 it goes to 4, okay, in the pump. So it pump to the higher pressure. 5 combined with 8. Sorry, 4 combined with 8 become 5. Okay, 4 here combined with 8 here. So you got point number 5, which is saturated liquid. And then 5 to 6 is the pump. 6 it goes to 7 as a saturated vapor. Okay, and then from 7 it is expanded to number 10. From 7 it expanded to number 10, but along the way Y fraction is extracted, Z fraction is extracted, and the remaining is 1 minus Y minus Z. So this is the TS diagram for this process. Okay, in terms of analysis, we are looking at the net power output and the thermal efficiency. Okay, by definition, the net power output is given as W out minus W in. W net is W out minus W in. Okay, or we can also use this equation, W net equals to Q in minus Q out. So you have two equations here. Okay, this is the common one. W net should be W out in the turbine minus W in from the pump. Okay, or we can also use the equation W net equals to Q in minus Q out. So if you look at this equation, you might be asking, how do I get to that equation? So you have to recall back. I mean, let's recall back on our fundamental of heat engine diagram. Okay, so if this is heat engine, this is the high temperature source and low temperature sink. You have W out here, and then the source supply Q in to our heat engine, process the heat, produce work, and at the same time you have to dump some of the heat to the sink. So that is Q out. Okay, in terms of the direction of heat transfer, you have this direction. Okay, so the direction into the heat engine, and then you have two direction coming out of our heat engine. So we can do the balancing of equation here by taking a heat engine as the node. The summation of all the inlet equal to the summation of all the outlet. Okay, based on this. So we have only one in, which is Q in. Q in equals to W out plus Q out here. So you can manipulate that equation. W out equals to Q in minus Q out. So this is how we can find this equation. W out or W net out equals to Q in minus Q out. So you want to find W net, right? We can simply use Q in minus Q out. From this diagram, our Q in is in the boiler from 6 to 7. Our Q out is in the condenser from 10 to 1. So that is fairly straightforward if we use this equation. Okay, W net equals to Q in minus Q out, whereby Q in here is H7 minus H6. Okay, in the boiler here, this is 6, this is 7. 7 minus 6 is our Q in, and Q out, you have H10 minus H1, right here, H10 minus H1, but the mass flow rate in the condenser just now is 1 minus Y minus 7. You have to multiply by 1 minus Y minus 7 because it is not 100%. So this is our Q out. Okay, if we want to use this equation, you can. Okay, but then you have to find W out, which is in the turbine, and W in, which is from the 3 pumps. So by looking at the condition for W out and W in here, you have to do a lot more analysis for the 3 pumps and 1 turbine. So it is much simpler if we can use W net equals to Q in minus Q out. Right, so this is the equation that you want to solve, Q in and Q out. Okay, the problem now is that you have to identify what is Y and Z, the fraction. Okay, the fraction of mass flow rate. I think H7, H6, H10, H1 and all the enthalpies, you can simply get them from the steam table. Now, find the values of Y and Z. So to find the values of Y and Z, you can simply apply the energy balance to the feed water heaters. Okay, feed water heater number 1 and feed water heater number 2. We can start off at the feed water heater at number 2. So if we refer to the schematic diagram, at feed water heater, okay, feed water heater at point number 2 here, you have Y fraction coming in, and then 1 minus Y fraction coming in, and then you have point number 5 as the outlet. So I can just redraw back the condition. Number 8 coming into the feed water heater, number 4 coming into the feed water heater, and then number 5 coming out of the feed water heater. So you have Y fraction through point number 8, 1 minus Y fraction through point number 4. Usually the feed water heater is insulated to prevent heat from coming out. So I just demonstrate here how do we apply energy balance to the feed water heater number 2. Okay, energy in minus energy out equals to delta E of the system. This is an open system, steady flow. So delta E of the system equals to 0. You end up with E dot in equals to E dot out. Okay, all the energy coming into the feed water heater equals to all the energy coming out of the feed water heaters. And then we can start putting in all the necessary terms for energy in and energy out. Okay, remember energy can be transferred by Q, okay, by W and by M theta, where theta is the enthalpy plus kinetic energy half V squared plus G Z. Okay, and then if we put the dot, now everything become a rate, kilogram per second or kilojoules per second or kilowatt. So you can list down all the Q, W and M theta here, and then we can start cancelling the term. This is a mixing chamber. Open feed water heater is a mixing chamber. We allow the mass to mix. Okay, mass of hot water and cold water, they can mix inside. So usually they are insulated. So Q equals to 0. Here, both in and out. No Q in, no Q out. Feed water heater, there is no work done or work in or work out. So you can cancel the W term. And then in terms of the enthalpy term will be significant. Okay, the kinetic energy term, the kinetic energy, okay, the flow of steam coming in, the flow of steam coming in from number 8, from number 4, and then it goes out. So the kinetic energy difference will be more or less similar. We assume that the velocity coming in and coming out should be more or less similar, so you can just cancel the term. And then in terms of the potential energy difference, they should be the same. Okay, the potential energy in and the potential energy out should be the same. They are function of the elevation. Usually the feed water heater is located at certain location, so you are measuring the Z here. The Z for the inlet and outlet should be more or less similar, so the change is 0. So you have cancelled almost all the term except for the enthalpy. So the summation of all the mass in, MH times H in equals to the summation of all the mass out times H out. Right, so based on the point, I can say that M8 H8 plus M4 H4, these are the inlet. M8 H8 here and M4 H4 here equals to M5 H5. This is what coming out. Okay, for number 8, you have Y fraction, so you have to multiply by Y. Y times H8 plus, okay, at point number 4, the mass fraction is 1 minus Y. At point number 4 here is 1 minus Y. At point number 8, it is Y. So you can just put in Y times H8 plus 1 minus Y times H4 equals to 100% mass coming out, 1 multiplied by H5. Okay, and then we manipulate that, YH8 plus H4 minus YH4 equals to H5. And then you rearrange to find the fraction of y to be equal to h5 minus h4 divided by h8 minus h4. So you can now here you can solve for y. To solve z, okay, let's say you want to find z, we can use our feed water heater number 1, okay, which is also insulated. So if we look at feed water heater number 1, here you have Z coming in, okay, Z mass fraction coming in at point number 9, and then 2 coming in with the mass fraction of 1 minus y minus Z, and then 3 coming out with a fraction of 1 minus y. So you can translate that in the forms of simple illustration here. Okay, this is point number 9 here. This is point number 2, and this is point number 3. Okay, Z mass fraction at number 9, 1 minus y minus Z mass fraction at point number 2, and 1 minus y fraction at point number 3. Okay, similar concept, we apply energy balance. And then you can start cancelling all the term except for the enthalpy term, which is significant here. You cannot cancel the enthalpy term. Okay, summation of M in H in equals to summation of M out H out. So you have, the M at the inlet is point number 9, M9 H9. Okay, number 2 also coming in to the feed water heater, M2H2 equals to at point number 3, which is M3H3. Okay, the fraction must be included, so you have Z multiplied by H9 plus 1 minus y minus Z multiplied by H2 equals to 1 minus y multiplied by H3. So this is the function or the equation for to find Z. Okay, if I elaborate this, I will get, let's say you have Z. Okay, let's say you have Z H9 plus H2 minus y H2 minus Z H2 equals to H3 minus y H3. Okay, just rearrange for Z. You have Z H9 minus H2 plus H2 minus y H2 equal to H3 minus y H3. Okay, you can just separate the variable. H9 minus H2 equals to H3 minus y H3 plus y H2 minus H2. Okay, so here you can have Z equals to H3 maybe 1 minus y plus H2 y minus 1 divided by H9 minus H2. So this is the function for the Z. Okay, now we can find all the properties at each of the point. Okay, for the schematics, so we have point 1, 2, 3, 4, 5 until point number 10. Okay, 1 to 2 is in the pump, so we know that at point number 1 it is HF or saturated liquid at 5 kilopascal. So H1 equals to HF at 5 kilopascal, which can be obtained directly from the steam table. So if we are looking at table A4 for the mixture, okay, we find the table of pressure. Okay, for 5 kilopascal, these are the properties. So I am interested in HF. So HF is here, 137.75. Okay, 137.75 kilojoules per kilogram. And then at the same time, I can also find the specific volume, which is similar, VF at 5 kilopascal. Again, you refer to the specific volume table, which is VF, which is here, 0.001005. So you have 0.001005 meter cube per kg. Okay, to find properties at number 2, we can use the relationship H2 minus H1 equals to V1 P2 minus P1. Okay, and therefore H2 equals to H1 plus V1 P2 minus P1. Right, and I can just substitute the numbers, 137.75 plus specific volume 0.001005 multiplied by P2 minus P1. Okay, pressure at 2 and pressure at 1. Pressure at 1 is 5 kilopascal. Pressure at 2 is the feed water heater pressure, which is 0.2. Okay, 0.2 megapascal. So P2 is 0.2 megapascal, which is 200 kilopascal minus 5 kilopascal. So you have H2 equals to, put it in the calculator, you have 137.95 kilojoule per kilogram. So that is H2. Okay, and then we can repeat for point number 3. At point number 3, we know the pressure at 3, which is 0.2 megapascal. Okay, we're looking at pressure number 3. number 3 is here. Okay, bear in mind just now that the liquid that goes out from the feed water heater, they exist as a saturated liquid. So we know pressure at number 3 is 0.2 megapascal, and then we know that it is in the saturated liquid. Okay, from these two information we can find H3. Okay, at 0.2 megapascal saturated liquid, so 0.2 megapascal is around 200 kilopascal. So this is our 200 kilopascal properties. Okay, we find enthalpy. Enthalpy should be HF, so which is 504.71. So you can have enthalpy at 3 is 504.71 kilojoules per kilogram. Okay, maybe you can, or we need VF as well, because later on you want, it is in the pump, so you want to compute point number 4, you will be requiring the specific volume. Okay, specific volume at point number 3 is VF at the pressure of 0.2 megapascal. So we refer to the same steam table. VF is here, 100.1061. 100.1061 meter cube per kg. Okay, and then we can use the relationship V4 minus, sorry, not V4 but instead H4. H4 minus H3, which is work in second pump, equals to V3 P4 minus P3. So from here we can have H4. H4 equals to H3 plus V3 P4 minus P3. So our H4 would be H3 504.71 plus 0.001061 multiplied by P4 minus P3. So the pressure at 4 and 3, pressure at 3 is 0.2 megapascal, pressure at 4 is 0.6 megapascal. So you have 0.6 megapascal is around 600 minus 200. Okay, put that in the calculator, you should get H4 equals to 505 kilojoule per kilogram. Then we jump to point number 5, where we know the pressure. P5 is 0.6 megapascal. Right. Now we know that it is in the saturated liquid. Okay, point number 5 is here. exit feed water heater as a liquid form as stipulated by the question. Pressure is 0.6 megapascal. So from here you can find your H. Okay, H5 equals to HF at 0.6 megapascal. So 0.6 megapascal is 600. So you are talking about this. You want enthalpy HF here, VF here, 670.38, 670.38 kilojoules per kilogram, and then V5 equals to VF at 0.6 megapascal. Direct from the steam table, 0.00 1101, 0.00 1101 meter cube per kilogram. Then for point number 6, it is in the pump. 5 and 6 is in the pump, so I can say that H6 minus H5 equals to V5, P6 minus P5. Okay, and then from here you can find H6 equals to H5 plus V5 P6 minus P5. Substitute the numbers. 670.38 plus 0.001101. P6 is the highest pressure, 10 megapascal, so that would be 10,000 kilopascal minus 0.6 megapascal, which is 600. Okay, in the calculator you obtain H6 equals to 680, okay, 0.73 kilojoules per kilogram. Okay, and then you can find point number 7. Number 7 is after the boiler, so you have P7 equals to 10 megapascal, and then you have temperatures at 7 equals to 600 degrees Celsius. From here you can find H7. So go to the steam table, 10 megapascal, 600, I think it is in the superheated. 10 megapascal here. Okay, so this will be the table. 10 megapascal, 600 degrees Celsius. So this is 600. We are looking for enthalpy. So VUHS enthalpy is 3626. 3626 kilojoules per kilogram. Then maybe we need S7, 69 6.9045 kilojoules per kilogram per Kelvin. So that would be the 7. Then point number 8, we know that pressure at number 8 is 0.6 megapascal. Okay, it means 7 to 8 is in the turbine. So we are assuming isentropic. So we know that S8 equals to S7 equals to 6.9045. So we know the pressure, we know the entropy, we can decide the phase. At 0.6 megapascal, okay, look at the mixture table. At 0.6 megapascal, 600 just now, entropy, okay, SG is 6.7, SF is 1.9. Okay, but our S here is 6.9. 6.9 is above this one, so it is in the superheated. Superheated steam. So we can refer to the superheated table, 0.6 megapascal, which is this one. Okay, 0.6 megapascal, 69045. Entropy 69045, 696. So the values should be in between these two numbers. Okay, we are interpolating the entropy and also enthalpy. So to make things clear, you can just put in enthalpy and entropy. So you have 2756.2, 2756.2, 67593. Okay, 6.7593. And then the entropy that we are looking for is 6.9045, 69683, 6.9683. This is the enthalpy at number 8. And the corresponding enthalpy at the bottom, 2850.6. 2850.6. So this is the table that you want to find. Okay, we are interpolating H8. So H8 minus 3756.2 divided by 2850.6 minus 2756.2 equals to 6.9045 minus 6.7593 divided by 6.9683 minus 6.7593. Okay, key in everything in the calculator. should be able to get the answer. Let's try it. 6.9045 minus 6.7593 divided by 6.9683 minus 6.7593. Okay, 2850.6, 2756.2 plus 27, so 2821.8. So it is 2821.8 kilojoules per kilo. Okay, we are done with point number 8, and then we go to point number 9. Okay, point number 9 is here. Pressure is 0.2 megapascal. Okay, it is still in the turbine. Right, from number 7 it goes to number 9. Okay, but the pressure is 0.2 megapascal. So we know that P9 equals to 0.2 megapascal. And then since 9 is exiting the turbine, we know that S9 equals to S7. Okay, equals to 6.9045. 6.9045. I think we have to guess the phase. So let's have a look at the mixture table. 0.2 megapascal, 200 kilopascal. Okay, 200 kilopascal, SG 7.1, SF is 1.5. So our S7 is 6.9. So 6.9 is in between these two numbers. So it is in the mixture. So we know that it is in the mixture region. We can compute X9, okay, by using entropy. S9 minus SF divided by SFG. Okay, 6.9045 minus SF at 200, 1.5302. 1.5302 divided by SFG 5.5968. 5.5968. Okay, so you put it in the calculator. You got your X9 equals to 0.69. Sorry, 0.96. Okay, once you got X, you can find H. H9 equals to HF plus X9 HF G equals to HF can get it here, 504.71. Okay, 504.71 plus x 0.96. HFG, refer back to the steam table, 2201.6, 2201.6. So your H9 is 2618.7. And the last one is for point number 10. Okay, the condenser pressure P10 is 5 kilopascal, and then you can use the entropy constant, S10 equals to S7 equals to 6.9045. So you can check the phase, 5 kilopascal. SG is 8.3, our S is 6.9, so it is in the mixture as well. Right, find X10 by using entropy, SF minus, sorry, not SF but S10, S10 minus SF divided by SF G. Can refer to the steam table for all the properties. S10 6.9045. SF from the steam table, SF is 0.4762, 0.4762 divided by SFG 79176, 79176. Right, you have X10 equals to, put it in the calculator, 0.81. Then you can find H10, which is defined by HF plus X10 HFG. Okay, everything is from the steam table. HF here 137.75, 137.75 plus 0.81, HFG 2423 from the steam table. So you have H10 equals to 2105 kilojoule per kilogram. Okay, once we obtain all the properties, then the rest is fairly straightforward. You can just substitute the numbers. So let's say just now we have Q in equals to H7 minus H6, Q out 1 minus Y minus Z, multiplied by H10 minus H1. So H7, H6 is already obtained from the steam table. Our Q in is 2945.27 kilojoules per kilogram. Okay, to find Q out, somehow we need to find what is Y and Z. Y is given by H5 minus H4 divided by H8 minus H4. So you can substitute the numbers. 548. So H5 is 67038. H4 is 505. So we can just put in the numbers 670.38, H4 is 505.13 divided by H8, 28, 21.8. That is H8. Let's double check that again. H8, 28, 21.8 multiplied by minus by 505.13. So you got y equals to very small numbers, 0.071. 0.071. So that is the percentage. I think, and then for Z, that is very straightforward as well. Z equals to H3. What is H3? 504.71. 504.71. 1 minus Y, 0.071 plus H2. So our H2 137.95. 137.95. Y minus 1, 0.071 minus 1. H9 minus H2. 3617. 18.7 minus 137.95. Okay, put in the calculator and check. Got 504.71 into 1 minus 0.071. Okay, plus 137.95. 0.071 minus 1 divided by 261857 minus 137.95. So you got 0.1373. Okay, that is our Y and Z. Okay, and then you can find Q out equals to 1 minus Y minus Z. 1 minus Y minus Z, 0.1373 multiplied by H10 minus H1, H10 2105 minus H1, the earliest part, 13775. Okay, then you can get your Q out. 1 minus 0.071 minus 0.1373 multiplied by 2105 minus 137.95. 1557. Q out is 155. Let's say 1557 kilojoules per kilogram. So W net is Q in minus Q out. Q in minus Q out equals to 29.45 minus 1,557 equals to 1388. Okay, so your megawatt W dot net should be M dot multiplied by W net. Okay, equals to 22 kilogram per second, 1388. You got approximately 30.5 megawatt. That is W dot net. And the last one, to find the thermal efficiency, it is simply 1 minus Q out divided by Q in equals to 1 minus Q out 1557 Q in 29 29.45.27. Okay, that will give you, put in the calculator, 47.1% approximately. Okay.